Hi everybody, we're doing the net force practice problems once again. And we're going to start with number one, which you got Sarah weighing 750 newtons, that's not pounds. And so she weighs 750 newtons. So in my little drawing here of Sarah on the swing, she would actually have a downward vector in a free body diagram of 750 newtons going down. Okay? And I want to know how much tension is on each individual rope. So I'm going to have rope number one up here. This is going to be rope number two. The issue is this is sort of a weird swing because the ropes do not pull straight up and down. They simply pull at a 55-degree angle. On all these problems, we're going to start off with a single formula, but the formula is not the same every time. Here's what I mean with that. We're going to start off with this Greek letter that says sigma. Sigma means the sum of. And so I'm going to start off with the sum of all the forces. And what you have to do is you have to draw a diagram and then write down all the forces that are on the object. So it's always going to be different no matter what problem you do. Well, on this swing, the sum of all the forces are this. You have the force of number one plus the force of number two plus gravity, which pulls down. And so now we're going to put all these in. Well, you got to remember that force one and force two are both pulling at the same angle, so we can say that they're the same force. So I'm going to now rewrite this as 2 times F, because both of those forces are the same, plus the force of gravity. Well, if you look at this, all of these forces have to be pulling in the same direction. Well, this sort of stinks because gravity pulls straight down, but these strings are pulling up at a 55-degree angle. So you're going to have to use some of that trigonometry that we learned during the vector chapter. And so if you look at this string right here, this one pulls up in the x direction right along that green line. It pulls in the, instead of x direction, I mean the y direction. It pulls in the x direction, the amount of that blue line. Well, if I'm looking for the green line, that's the opposite side. But force number one is actually the black side going along a diagonal like this. Okay, so that's force number one. Let me go ahead and make that black so we know that it's the diagonal that's force number one. And this diagonal over here is force number two. So if I want to use gravity in this formula, which goes up and down, all of these forces must be in the y direction. So that means I need to change this one right here. So watch what I do. I'm going to do the sum of all the forces in the y direction. Well, if you want to find the y direction of this right triangle right here, we're going to have to find the opposite side. And hopefully you remember from trig that the sine of the angle equals opposite over hypotenuse. Well, F is our hypotenuse. So I need to find the opposite side. We'll cover up that O, and it gives you the formula of, I'm going to bring down my 2, and the F is going to be the opposite side. Now I'm going to put the sine of the angle times the hypotenuse plus FG. So now we've got to plug in all these numbers here. Well, since she's not moving, all the forces have to add up to 0. Bring down my 2. The sine of the angle is 55 degrees. The hypotenuse is F1. And the gravity is 750, but since it's pulling down, we got to make this a negative 750. So now I'm going to do all this funky math here. When you put in the 2 times the sine of 55, you end up getting 1.64 F plus negative 750. I'm now going to add 750 to both sides. I'm just going to bring this right up here. So I add 750 to both sides. That gives me this. And now divide both sides by 1.64 to get F by itself. And so the force of tension on both sides ends up being 457 newtons. Okay, now I'm going to go on to number 2, and every time I do these problems, I'm going to draw it first. I'm going to draw a person standing on a scale in an elevator. So here's my dot. The scale is going to push up, so it's going to be my force of the scale right here. And gravity is going to push down. That's my 2 forces that I have on there. So once again, you're always going to start off with the same formula of the sum of all the forces, and you simply write those down. Well, you have the force of the scale plus the force of gravity. Well, it says, what is the apparent weight on a scale when the elevator is accelerating with an upward acceleration of 2 meters per second? Well, they didn't give you any forces here. They gave you the acceleration. So when you don't know something, you have to substitute in another formula. Okay? Well, let's figure out what we can substitute in. For force equals mass times acceleration. The force on the scale is what I'm trying to find, since that's the apparent weight on the scale. So I'm just going to put down the force of the scale right here. I'll just put a little s there. And the force of gravity, well, they didn't give me the person's force. They gave me the mass of the person. So gravity, the weight of the person, equals mass times gravity. So what we have to do now is we have to put in all of these numbers. Well, the person's mass is 100. It says that the person is accelerating upward with an acceleration of 2, so I'm going to put in a 2 meters per second right there. It's positive because it's going up. I'm going to bring down my mass for the weight right here of 100, and gravity is negative 9.8. So now when I do the math, I'm just going to bring it right back up here. I now have 200 on the left-hand side equals the force of the scale plus a negative 980. Whoops, negative 980. Well, now I have to add 980 to both sides to get FF by itself, so the force on the scale is actually 1180 newtons. So when you're going up on an elevator, you will actually weigh more. That's where you feel like you're pushing against your feet and feel a little heavier. Now let's do part B. It's going to be the same exact formula, but now the elevator's going down. Well, I can go ahead and just use the same stuff here. I'm going to do all the same exact formula again, but instead of putting 100 times 2, I'm going to put in 100 times negative 2 because the elevator's going down. I'm still trying to figure out the force on the scale. It's down in the library. I'm going to have 100 times negative 9.8 because gravity's still pulling down. So if you do the math, you got negative 200 equals the force on the scale minus 980. I'm now going to add 980 to both sides. And so now the force on the scale equals a positive 780. So when you're going down on an elevator, you actually feel like you weigh less. Well, what would happen if you're absolutely in free fall? There's no force acting up on you whatsoever. Do the same exact formula again, but if you're in free fall, that must mean you must be falling an acceleration of negative 9.8. Okay? I'm going to bring down my Fs plus a mass of 100 times the gravity here, negative 9.8. Let's look what you have here. You got negative 980 equals Fs plus negative 980. I'm going to add 980 to both sides, and the force on the scale equals 0. So when you are when you're in free fall, you are weightless. And that's why the water stopped coming out of the bottle when we dropped it out the window in class. That's why the astronauts are weightless as they fall around the Earth when they're in orbit. So this explains why you have 0 weight. It's not because there's no gravity. There's plenty of gravity there. It's still 9.8 meters per second squared. But since there's no support force, you have a weight of 0. And on number 3, it says, what is the weight? So I'm looking for the weight. And I happen to know that weight equals mass times gravity. I'm just going to write that down real quick. That requires a 50 newtons, so my force is 50 newtons. I'm going to put that down here. To accelerate it, so acceleration is 2 meters per second squared, on a frictionless floor. So once again, I'm trying to find the weight. So I need to know, I got gravity, I just need to know the mass. Well, look what I got here. If I need to know the mass to find weight, I have force and acceleration. So let's remember this formula that we have here of F equals ma. And so if I want to find mass, I'm just going to take F divided by A. My force was 50 newtons. My acceleration was 2 meters per second squared. So that gives me a mass of 25 kilograms. Well, what can I do with that? I can take that 25 kilograms and place that right here in this formula. So I'm going to take W, which is weight, equals mass times gravity. So I take the 25 kilograms times 9.8 meters per second squared. You multiply that together, and you end up getting 245 newtons. Okay, finally, on number 4 here, it says a 10 kilogram box. So I'll put a box on the table. Is being pulled by a 2 kilogram mass. I got 2 kilograms hanging off the table. It's hanging from a string. What is the system's acceleration? Well, if you remember, I told you to always start with the sum of all the forces. So I'm going to start with the sum of all the forces. And the only force that I have on this system is this 2 kilogram mass here. So it's going to be mass times gravity. It's the only force that you have is the force of the weight. And so what I'm going to do now is I'm simply going to plug in everything that we got. All right, so they need to know they want to know the mass or the acceleration of this system here. Well, there's no acceleration except for gravity in this formula, so I need to change the sum of all the forces to mass times acceleration. I'm going to put this as mass times gravity over here. Now you got to be really careful because these two masses are not the same. This is the sum of all the masses. So if you were to sum up these masses, see how it's a sum of all the masses? Okay, I would have the 10 plus the 2. So 10 plus 2. And it's the acceleration of that whole thing. Now, this right here is the force that's actually pulling it. Well, the mass that's pulling it is 2. And it's being pulled by gravity, which is negative 9.8. I'm just going to put in 9.8 right now because it's pulling it to the right, so I just kept that positive. And so to get acceleration, I'm going to take 20. Try this again, Jeff. I'm going to take 12 times A equals 19.6. Divide both sides by 12. And my acceleration ends up equaling 1.63 meters per second squared. Now, most of the time you don't do it this way. I actually want you to do an X system and a Y system. In other words, you'll do a formula like this in the X direction and a formula like this in the Y direction. And I'll show the AP how to do that in a second. But since this pulley system right here is making all the Y turn into X, in other words, the Y pulling down actually is the same as the X getting pulled across, I can just simplify that equation like that.